So acids always give up a hydrogen ion when you put them in a solution. So you can see in my example, if you take hydrochloric acid and water, combine them together, the HCl gives up its H, combines with the water to form what they call a hydronium ion, and then the chloride ion. So you can see how this is the acid. In this example, because HCl ends up becoming just the Cl minus, so the acid always loses the hydrogen ion. And in this example, the water acts as a base because it gains it. So this is sort of what I always look for if I'm looking to figure out what's an acid, what's a base in a solution. The one that loses its H or its hydrogen ion, that is always the acid. So kind of like oxidation and reduction, remember that you always had to look at the reactants and then kind of look at what happens on the product side. So you always define the acid as being one or the other reactant. The acid's always the one that loses its H in the reaction. The base is going to be the one that gains it. So in this, remember then, if acid is present in a solution is going to have water, so the acid is always going to give its hydrogen ion to the water molecules that are around. And so water, in the presence of an acid, always becomes what they call the hydronium ion. So just remember that it just means that it's water with an extra hydrogen because of the acid that's about, the acid that's around it. So if water is in the presence of an acid, it always accepts or pulls in those a hydrogen ion, so it ends up looking like an H3O+. So it looks like water with an extra hydrogen. That's the hydronium ion. But then remember bases. Bases, they produce the ion that's called a hydroxide ion. Hydrogen ions are acids, hydroxide ions are bases. Bases taste bitter. Bases feel real slippery on your skin. Further, the description of what a base does, if it comes in contact with an acid, bases act as hydrogen acceptors. So in this one example, you see that if you take a molecule like sodium hydroxide, put it in water, it splits into ions and it makes those hydroxide ions. But then also, if you have a base, it will end up being the one that accepts or takes on the hydrogen ion from the acid. And in this case, it ends up making salt and water. So they say it's a proton acceptor or a hydrogen acceptor. You can also think of it as it's the one that gains the hydrogen. The OH pulls the hydrogen in to form water. So here's a couple of other examples for this one. So in the top one, if you look at hydrogen chloride and water, notice that as you progress across, hydrogen chloride just ends up becoming just the chloride ion. So you see that it loses hydrogen. Since it loses hydrogen, that makes it the acid. In this case, water becomes H3O+, so water gains a hydrogen, so water acts as a base. So just remember that the acid is always going to lose its hydrogen on the reactant side, and the base is going to gain. So then when you look at the one at the bottom, so the one at the bottom, ammonia and water, making the ammonium ion and the hydroxide ion, you can see that ammonia, NH3, becomes NH4+. So you can see that it gains its hydrogen ion, so that makes it a base, The water becomes the OH minus. So water loses a hydrogen, so it goes from H2O to OH. So it loses a hydrogen. So that makes the water an acid. So remember that when you look at these, look at the reactant side and just compare what happens to this molecule in the reaction. The acids will always lose a hydrogen, the bases will always gain. So then I gave you a couple of strong acids, ones that you've seen in lab, like sulfuric acid, hydrochloric acid, nitric acid. Those are 3 ones that we used over the course of the semester. Sodium hydroxide is a strong base. Potassium hydroxide is another one, so NaOH and KOH, 2 strong bases. So remember, if it's strong, that means that they're a strong electrolyte. So remember back in chapter 8, if it's a strong electrolyte, the arrow goes from left to right, always. Arrow goes in one direction. 100% of ions are formed. So the acid's completely split up into ions. The base is completely split up into ions if they're a strong acid or base. So they have 100% form ions. Remember that in a strong electrolyte, the arrow goes from left to right. Now the kicker with these is if you're talking about a strong acid or a strong base, this means that they're going to make 100% hydrogen ions or hydronium ions, 100% hydroxide ions, and these are very reactive ions. So the H+, or you could also think, remember, if there's water involved at all, it's always H3O+, the hydronium ion. These, or the hydroxide ions, are very reactive. They can cause damage to tissues, which is why you try to limit your exposure to strong acids and bases. They call that corrosive. So if you see the word corrosive on a bottle, then you know that it means that it contains chemicals that are reactive to body tissues. Good chance that they might be a strong acid or base. So prolonged exposure can actually cause tissue damage and could even cause chemical burns. So that's why we just use them in really small amounts. If I have a high concentration of hydrochloric acid or sulfuric acid, I would leave it in the hood. It would be something that you wouldn't have set out. So there's just characteristics with strong acids or bases. Difference though, you can also have a weak acid or a weak base. Weak electrolytes, remember the arrow goes both directions? If it is a weak acid or base, they only partially form ions, and the word they use is dissociate, which really the word dissociate just means it forms ions, but it only does this a little bit. So remember I said only 5% form ions, 95% remain as a whole molecule. This is also when you always will see the arrows going both directions. Right, so ways to pick it out. Arrows going both directions show you it's a weak electrolyte, a weak acid or base. So if it's a weak acid or base, then you don't have as many ions. So these are less corrosive, even in higher concentrations. So that's why you can put vinegar on your food. Vinegar is an acid, but it's a weak acid. So therefore it's not as corrosive, would cause less damage to tissues. Same thing with the strong bases. Strong bases, I said they're dissociate 100%. They can be corrosive. You try to limit your exposure. Weak bases, on the other hand, like NH3. So NH3, when it's mixed with water, does not form 100%. It just partially dissociates, but you end up with NH4 and that OH minus, the hydroxide ion. But notice you got the arrow going both directions. And that's like ammonia, the household cleaner ammonia. It is a weak base. It's super strong smelling though. So if you've ever gotten a really big whiff of ammonia, it's very strong smelling. But in fact, it is a weak base compared to sodium hydroxide, because NaOH is going to be 100% ions, is much more reactive to tissues. When you take an acid and a base and mix them together, they neutralize each other because the acid, the hydrogen ion of the acid, the H plus, and the hydroxide ion of the base, both very reactive, but when they combine, H and OH make H2O. So it ends up forming a very neutral molecule that doesn't have any of the characteristics of those ions. It's not corrosive, it's not reactive with body tissues. So you can see it in this one. So just remember, if you're talking about a strong acid and a strong base, if you mix them equally, a salt and water are formed. So this could be any strong acid, any strong base. When they neutralize each other, they form just a salt and water. So I could take like H2SO4 and potassium hydroxide. H2SO4, sulfuric acid, potassium hydroxide. Sulfuric acid's a strong acid, potassium hydroxide's a strong base. In this neutralization, the outside pairs and the inside pairs will combine. So it's kind of like a double displacement. Remember when you had two compounds and they'd swap their partners? So in this, the H and the OH combine, just like here, the H and the OH. So see how those are kind of like the outside pairs? And then the inside pairs, so in this, the SO4 and the K combine, the Cl and the Na combine. So the outside pairs and the inside pairs combine. Sodium and chlorine, they're a 1-to-1 ratio because you know that sodium's a positive, the chlorine's a negative. So in this one, you would put potassium first. The K goes first because potassium is the metal. Potassium is in group 1, so you know it's a +1. The SO4, that's the sulfate ion. And remember, it has a -2. So what would the formula be for that product? How many potassiums would I need? Remember how you do that? Remember you assign the charges and then? So you'd swap them. So that -2 tells me that I'd have 2 potassiums. Potassium's a +1, so that means I only have 1 sulfate. So it would be K2SO4. That is a salt. And the other product is well, the H and the OH. It doesn't matter if I have 2 H's over there. It'd still just be 1 H and 1 OH, so that would make water. So the outside pairs form water, the inside pairs form the salt. Now you would have to go back and balance that, right? Because you see the potassiums aren't balanced, the water, the hydrogens are not balanced. So there would be balancing of the molecule that you'd have to do. But you could take any strong acid and base and react them, and they would always form a salt and water. They would always take 2 corrosive, reactive molecules and make something that is very neutral, very stable. Now, if you've ever had acid indigestion and you have taken an antacid is a base, but it's not a strong base, it's a weak base. And the reason why you use it is because you don't want to ingest a strong base. You wouldn't want to ingest sodium hydroxide because it's corrosive. It would damage your mouth, your throat, your esophagus, your stomach, before it ever reached the excess stomach acid. So instead, an antacid is a weak base, and that will not react with the lining in your mouth or in your esophagus. And once it gets down into the stomach, though, it will still react with the excess stomach acid. So magnesium hydroxide, that's found in milk of magnesia. It's also one of the components you find in Rolaids. Magnesium hydroxide will still react with hydrochloric acid, that excess stomach acid, and notice that it still makes a salt and water. So it helps to decrease the amount of acid present in the stomach, and that helps to relieve the acid reflux, the stomach irritation that you would otherwise have. Calcium carbonate is another one. Calcium carbonate is commonly found in Tums. In our lab, when we did this, calcium carbonate was the one that we found in the generic as well. But also, so calcium carbonate, it's a weak base. It reacts with excess stomach acid, and it still, again, makes salt, calcium chloride. The only difference is anytime you use a carbonate, you'll have carbon dioxide gas produced. So see that it's one of the products, and it's just because of the polyatomic carbonate ion ends up having CO2 formed, and that's why a lot of times after you eat a antacid like a Tums or the generic, it'll actually make you burp afterwards, and that is because carbon dioxide is generated in the stomach and it's a gas. So it gives you this sort of sensation, you burp and you're like, oh, I feel a whole lot better. Well, that's actually telling you that this reaction is occurring as well. So that's why somebody takes an antacid. It's really just to try and get rid of excess stomach acid and the negative side effects that you have with acid indigestion. So now, what about if you have a weak acid and a weak base? They still react, but they don't react 100%. In this case, you end up with this double arrow. So we're first just going to use some real general examples of this. And remember, we talked about weak acids and weak electrolytes in the last chapter. And I told you if it's a weak electrolyte, your arrow goes both directions, which means in this reaction where nitrogen and hydrogen makes NH3 or ammonia, if I take nitrogen and hydrogen, they're both gases, and I put them together in a container, a few of the nitrogen and hydrogen molecules will combine and form NH3. It doesn't react 100%, so I end up with, if I start off in my container here, and I have N2, 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 and then H2, H2, H2. So say I have 4 of each. In this reaction, eventually I will end up with some NH3, but I still have a lot of N2. I still have a lot of H2 that'll be present and not reacted. So all 3 end up being present. Product and reactant are formed once we reach what's called equilibrium. So remember equilibrium, I told you about things move from high concentration to low concentration through diffusion and osmosis. So if you have an imbalance, the goal is things like to become more balanced. So same thing can happen in reactions that are reversible, is that you end up with, you start with all reactant. As you make product, you're going to reach this balance. The balance means that the forward reaction and the reverse reactions actually end up becoming the same rate. So the formation of product, which is the ammonia, and the rate of formation of nitrogen and hydrogen becomes equal. So the forward reaction and the reverse reactions become the same rate, and that's when they say the reaction is at equilibrium. Once we reach equilibrium, there's going to be no net change. So the amount of nitrogen, the amount of hydrogen, and the amount of NH3 in my container at equilibrium is not going to change. Now, if I apply some kind of change to a reaction that's at equilibrium, then that is going to cause a shift in my reaction. And so the person that studied this was Le Chatelier, that's his name. So it's a French guy. So Le Chatelier studied reaction systems once they reach equilibrium. So when I've already got this balance, so I have the amount of nitrogen, hydrogen, and NH3 at equilibrium in my container. If I change the amount of a reactant or I change the amount of the product, that's going to upset equilibrium. And so the reaction will then shift to try and balance it out. So we can think of it just with like A and B and C. So if I have A makes B, A plus B makes C. That's my forward reaction. So if I start off with nothing but A and B, and it makes, instead of it going completely to make C, at some point C is then going to start breaking down into A and B. So I'll have this forward reaction, but then I start to have a reverse reaction until I reach this point where there is sort of a ratio of A, B, and C in that container. So once I'm at this is equilibrium. So if I have this container and I have A. So we'll say that there's like 5 A's, I have 2 B's, and I have 4 C's. And that's the equilibrium ratio. Okay, they don't have to all be 50, 50, 50. They don't have to be exactly the same. But what you find is the amount of forward reaction and reverse reaction are taking place at the same rate. So Le Chatelier said, well, what happens if I like add A? What if I like pump some of A into this system that's at this balance? So he said if I add anything, the reaction will always shift away from whatever I add. So if I add A, if I add A to this, so if I add A, add a bunch more A, what will happen is some of those A's will react with remaining B and make C. So what will end up happening is this one and this one combine and make another C. That this one and this one combine to make another C. So the forward reaction will occur to try and balance it back out again. So he came up with a rule. And so he said, if you add anything to a reaction at equilibrium, the reaction always shifts away from whatever you add. So if one side of the reaction gains, the reaction always shifts away from whatever you add. So always think like if I add, it shifts away. So they both start with A. If I add a substance, it shifts away. So if I add reactant, the reaction shifts this way. The forward reaction will occur to try and rebalance equilibrium. So what if I add product? What if I add C? Yeah, so if I start adding C, so if I go C, start dumping C in, the reverse reaction will occur. So this C will now become an AB. This C will now become an AB. This C now becomes an AB to try and restore the relative amount of A, B, and C present in the container. So if I add product, that means that the reaction is going to shift which direction, forward or reverse? It's going to go to the left. It'll go in reverse. If I add reactant, the reaction will shift to the right or shift forward. So whatever I add, the reaction shifts away from whatever you add. It doesn't matter if you add reactant or product. So then he kept studying and he said, well, what happens if I take stuff out? So if I have this container now back at equilibrium with A, B, and C all in the container, what happens if I remove B? So I just go in and I start removing. So now these B's are gone. So equilibrium, there has to be a couple of B's. So in this, if I remove B's, then that means some of the C will break back down into A and B. So now this C will become an AB. This C will become an AB. To try and restore the relative ratio of A, B, and C present. So if I remove reactant, the reaction shifts towards whatever I remove. So if one side loses, the reaction will shift towards whatever you removed to try and rebalance it. So which direction? If I remove B, which direction does it shift? Does it shift in reverse or does it shift forward? It's going to shift in reverse. So it'll go that direction. If I remove C, so if I went and took 1, 2, 3. So if I took those C's out, I need to replace them. So which way will the reaction shift? Forward. So C's, this A, if I take C out, then A and B will make C. Then this A and B will make C. There's my container. To try and restore the ratio that's present. So if I remove product, then the reaction will shift forward. So I have an example or a little demo for you. I don't know what's the best place to stick it so that you can see it here. Okay, so I brought just some colored water. I think it's easier to see if you can see it with the color that's there. So I need like 2 hands. Since you're way over there, come over and help me. You can come up and help me. Okay, so first, we're gonna have a reaction where we're gonna say like the forward and reverse reactions are the same. So see, you've got 250 ml beakers. Okay, so these are the same. So this side, this is gonna be the reactant side. Okay, and this will be the product. So this is like the forward reaction. So first, we start off with nothing but reactant. Right, so everything is reactant initially. Okay, and so notice there's no product. So this is the product and there's the reactant. So what you would do is you're going to take your beaker, dip it, and do a forward reaction. Okay, so there's yours. And then you're going to take yours, but notice you got to do it like 1 and 1. Notice when I do this, there's like no reverse. Okay, so go forward. Okay, then you take this and you're going to dip yours. Now notice there's a little, right? So you can see that there's like a little. So you have to come up this side. And you'll pour yours. You can probably still stand. I don't think you're blocking that. Okay, so you're going to do one. So you dip. No, you don't dip until she's done. So go forward. Now you dip and go back. Well, that looks better. Okay, lay the beaker down. Pour it forward. Lay your beaker in. And go back. So do you see that the reverse reaction is speeding up? Like the amount in the reverse reaction is greater now than it was initially. Okay? Okay, go ahead and go back. Forward reaction. No reverse. Try not to dip it. No scooping. Just laying it down, picking it up. What's going to eventually happen?
Equilibrium.
Yeah. So eventually, do you see the volume of the forward reaction and the reverse reaction will be exactly the same? Then they could keep doing this all day long. Would there be any change? No. Once you reach equilibrium, the forward reaction and the reverse reaction will be exactly the same. Okay, so you see that? All right, so let's do this. So everybody always thinks that equilibrium means it's the equal amounts. So we actually will have a bigger forward reaction, a smaller reverse reaction. So do the same thing, so dip and pour. And now you're gonna dip and pour. I have like paper towels somewhere. Good. Blue food coloring everywhere. So what are you starting to see?
That one's getting less.
Uh-huh. But what about the volumes in the beaker, in the buckets or the tubs?
You're having more product, more volume.
Uh-huh.
More product?
Do you see there's more product? Okay. Eventually, we'll still reach equilibrium, right? Even though she's got a big beaker, she's got a little beaker, eventually, no matter how she dips her big beaker down, it can't pick up but so much because of the level of the liquid. So eventually you're going to reach a point where you will be at equilibrium, even though you have more product than reactant. And once you reach that, the amount in the big beaker and the amount in the little beaker will be exactly the same. And so it won't be equal 50-50. There's more product, but the rate of the reaction is the same. So you can reach equilibrium without having the exact same amount of reactant and product. And if I had them switch beakers, what do you think would happen?
Be more reactants.
Then the reactant volume would go up, okay? But I'd again get back to equilibrium. I would get to a point where her little beaker can only pick up so much, her big beaker can only pick up so much. They are moving the same volume back and forth. That's equilibrium.
They'll be able to do that, like.
And it looks like it's about there, because it doesn't, you can tell there's more product. It doesn't really look like there's much of a change in the total volume between product. There's definitely less reactant, definitely more product. Okay, all right, you can stop. So now let's think about what happens in making changes. So what if I took and I added another, what would happen? It'll come off eventually. It's just blue food coloring. I knew it would stain everything. Okay, and it shouldn't have, you shouldn't be colored because it's like it's in water. There's nothing but blue food coloring in water, I swear. So what if I came with another beaker of blue or another flask of blue liquid and poured it into the reactant side? What would happen?
Everything off the equilibrium.
Equilibrium would be off. So then when they started dipping, which beaker would have more liquid in it? The reactant side. So do you see that the forward reaction would speed up? That I would move more liquid? So if I add reactant, the forward reaction becomes greater. So that's this one, right? So if I add reactant, the reaction will begin to shift and make more product. So they say the reaction then goes away from what I just added. If I had taken this flask and I dumped water or blue liquid into this one, then the reverse would begin to happen and I'd eventually get back to the equilibrium. Not necessarily exactly the same, but the volumes would become the same for the forward and reverse reaction and you would say it's at equilibrium. What would happen if I just took and poured this out? So if I took this and I took this reactant away. So there. Now I've removed reactant and you started to do this. Which direction would the reaction be greater?
Reverse.
In reverse, right? So the little beaker would move more. The big beaker couldn't move anything because there's none there. So if I removed reactant, the reverse reaction would shift into play until you reach equilibrium again. So the goal is always to try and end up with this balance so the forward and the reverse reactions are exactly the same. So if I add reactant or product, the reaction always will shift away from whatever you add. And if I remove reactant or product, the reaction would always shift towards whatever I took out. So that's why they say if you remove reactant on this one, if I remove reactant, the reaction would shift like this. It would shift in reverse until I reached equilibrium again. So that's really all he found. Like this was like his big work.
If you had like 3 of those, would you be able to do an example like A plus B equals C and then W equals B?
Well, but see, you've got to think like in a reaction, A and B being the two reactants, that they're coming together to make C. So they're not in separate beakers, or separate containers. This would be like A and B together, and this would be C. So if I had like a double displacement, then that would be A and B, that could be C and D. So this would be kind of the arrow. So that everything that's a product is on this side, everything that's everything a reactant's on this side, everything that would be a product would be in that container. Okay? So that's what I find is the easiest way to remember is if it's at equilibrium, whatever I add, the reaction shifts away from whatever you add. So add causes it to shift away, A and A. Removing, though, causes it to shift towards whatever you remove. So let's look at a couple. So what about this one then? And here's one more before we go on. There's a third thing. The third thing is temperature. Because we have endothermic and exothermic reactions. So in a reaction, Le Chatelier found just think of energy or heat as a product or a reactant. So just treat it as if it's just one thing that's part of the reaction. So in this one, when nitrogen and hydrogen combine to make NH3, that generates heat. So heat energy is a product. So he just treats temperature as a product in this reaction. If I had this reaction, heat plus NH3 and H2O forms equilibrium with NH4OH. Now, heat is a reactant. So that's an endothermic reaction. This, the one at the top, would be an exothermic, right? So exo means to come out. This one is endothermic because heat goes in. So exothermic, think of heat as a product because energy is released. Heat energy is released. Typically, that means like the temperature goes up. Whereas if I'm talking about an endothermic reaction, then in this, heat is going to be a reactant. So it'd be over on the reactant side. And in this, most of the time, these reactions will actually feel cold because heat is used in order to speed the reaction or cause the reaction to occur. So if I have this at equilibrium, if you add heat, the reaction for the first one would shift the reaction to the left or towards the reactant side. But with the bottom one, if I added heat, the reaction would shift away from heat and it would shift towards the product side. So up here, if I add energy, or if I add heat, then the reaction would shift away from what I added and it would end up shifting to the left. For the bottom one, if I add energy or heat, then in this one, the reaction is going to shift away from the reaction side, so it'll shift to the right, towards the product. I just say, just think of heat or energy as being a product or a reactant. And it means the same thing then. Heat and NH3, heat and that NH3 and H2O at the bottom. Whether energy is a reactant or a product. So for this first one, in this first one, if I cool this reaction, that would remove what? That would be the same thing as decreasing the temperature, cooling the reaction would be like taking heat away, right? So if I heated something up on the top one, if I heated, it would actually shift the reaction to the left. But if I cooled the reaction, that's the same thing as removing energy or removing heat, and that would cause the reaction to shift forward. What about the bottom one? If I cooled this reaction, which direction would the reaction shift, to the right or the left? So if I cool this reaction, because heat is a product, a reactant, I'm removing reactant, that would cause the reaction to shift towards whatever I removed. So if I give you an example, one, I don't expect you to finish or complete a reaction in these, but if I give you an example like this one, NH3 plus HSO4 minus plus heat forms an equilibrium with NH4 plus and SO4 2 minus. Okay, so here's this one. You see that the reaction goes in both directions. Remember, I don't have that font. So when you see that, remember it means the arrows are going both directions. So I say, if the above reaction is at equilibrium, then I know I've got this forward and reverse reaction is balanced. Which way will the reaction shift if I add NH4? Will it go forward to the right or reverse to the left? So you tell me, if I add NH4 plus, If I add NH4 plus, that would be adding what it would cause it to shift towards what I just added. And what's the rule? Find NH4 plus. So here, for this one, if I add, then that means the reaction goes which way? It always shifts away from whatever I add. So if I'm adding, it shifts the opposite direction, away from whatever you add. What if I removed SO4 2 minus? So in this one, it's going to cause the forward. So if I remove, that means it's going to take it away. So whatever I remove, the reaction always shifts towards whatever you take out. So whatever I take out of the reaction shifts towards whatever I do, so it would be forward. So what about adding heat? So it's at equilibrium, and I add more heat. Yep. Because whatever I add, if I add this, it shifts away. So that would cause the forward reaction. So what if I took out HSO4 minus? Is it a reactant or a product? It's a reactant, so it's here. So if I remove, this comes out, that means that the reaction is going to shift which way? Yep, it's going to shift towards it. So it's going to be the reverse reaction. And then the last one, what if I add NH3? So if I add, the reaction shifts away. So that's going to cause the forward reaction to occur. And the goal is, it doesn't cause it all to occur, it just brings it back to equilibrium. So if I add something, then that makes it like more heavy on that side, so the reaction shifts to try and balance it out. If I take something away, then that means that there's less of it on this side, so the reaction shifts in reverse to try and bring it back into equilibrium, because that's really the goal. Is that we want to restore equilibrium. Well, acids and bases do this too, especially when we're talking about weak acids and bases, because they create this equilibrium. So in this one, remember we said an acid is the one that loses its hydrogen ion. So if you look at this first one, and the thing to do is find, so you see CH3COOH. Look on the product side and find the most similar molecule. Can you see that this is? Can you see those look a lot alike? Okay, so CH3COOH doesn't look like H3O plus. So those two definitely are the most similar. So they're actually considered pairs. They're pairs because they either gained or lost a hydrogen ion. So in the first one, CH3COOH becomes CH3COO with a negative charge. So this lost a hydrogen ion, right? It lost its hydrogen. That's why it's the acid, because acids lose their hydrogen. Then the same, if you look at the other reactant, H2O, and you find the most similar pair on the opposite side, it's H3O plus. So you would say that H2O gains a hydrogen to become H3O plus. So it gains that hydrogen ion. That's why it's a base. So we said, remember we said acids lose hydrogen, bases gain. But see the double arrow. So this actually reaches equilibrium. So there's 4 things in your container because there's reactant and product. It reaches the point of equilibrium where the forward and reverse reactions occur. So if the reverse reaction occurs, do you see that in the reverse reaction, CH3COO becomes CH3COOH. So if I look at the product side and think about the reverse reaction, do you see that it gains a hydrogen ion back? So in the forward reaction, the acid loses its hydrogen ion. In the reverse reaction, that product reforms the acid. So they say since it gains a hydrogen, that's characteristic of a base. But on the product side, they don't want to call it the base because then it gets confusing as to which one's which. So the forward reaction get identified as the acid and the base. The reverse reaction can get identified as a conjugate acid or base. So notice in this, the conjugates on the product side. The conjugate base is the product that gains the hydrogen ion. The conjugate acid is the product that loses it. So if I go in the opposite direction, do you see that this loses its hydrogen ion when it reforms water? So in the reverse, as well as the forward, you can identify an acid and a base pair. But here's the kicker thing to remember. So remember that you're always going to see that the acid, this is going to be the reactant that loses a hydrogen ion. And it becomes the conjugate base. So the product, the pair, the acid always forms the conjugate base. On the product side. And the base, H2O, how would you define it? The base is the reactant that gains the hydrogen ion and it forms the conjugate acid. On the product side. Because they're all present together when they're at equilibrium. You have all 4 of those types, so you can identify them. And if I add conjugate base, that would shift the equilibrium. If I added acid, that would shift the equilibrium because there are all four of them present in the container. If I upset the balance of equilibrium, then the forward or reverse reaction will occur to try and restore that. So let's practice a couple. So here's this one. So in this, and again, notice you have the arrow going both directions. I can't draw it any other way. HCN plus NO2 minus is at equilibrium with CN minus and HNO2. So first off, look at the reaction, pick out the pairs. So pick a reactant and then find its pair. The most similar pair. If the reactant loses a hydrogen, it's an acid. And then you know its pair is the what? The conjugate what? So the acid forms the conjugate base. If the pair gains a hydrogen, if the reactant gains the hydrogen, then you know it's a base. And over on the product side, its most common pair is the conjugate acid. So what is HCN? First off, what's its most common pair? CN minus. Everybody in agreement? Okay, HCN and CN minus, they look the most similar. So that makes this the acid, and that makes CN minus the conjugate base. Because CN minus gains a hydrogen in the reverse reaction, so it's a base. But you always define the products as conjugate bases. So then what about NO2 minus? Most similar pair is HNO2. Everybody agree? And what happens to it? So it gains a hydrogen, which makes it a base. And by gaining that hydrogen, it forms the conjugate acid. Okay, so look at the next one. Find the pairs. Figure out which one gains. The one that gains is the base. The one that loses is the acid. And then define their conjugate pair on the product side. Okay, so NH3, what was its pair? NH4 plus. So NH3 is the base. And so NH4 is the conjugate acid. Okay, so HSO4 minus. Its pair. So HSO4 and SO4 2 minus. So HSO4 is the acid. So see where it loses its hydrogen. So that makes SO4 2 minus the conjugate base. All right, try this one. You have this one. I just typed it out because it was handwritten. So you should see this looks very similar. I think I added one extra one. But pick these. Look at the pair. Look at the acid in its pair. Find the base in its pair. Okay, H3PO4. What's its most similar pair? So that makes H3PO4 the acid. Okay. That means that H2PO4 minus is the conjugate base. H2O. So H2O becomes H3O plus, so it gains a hydrogen. That makes it the base. And so H3O plus acts as the conjugate acid on the opposite side. And remember, the conjugate just means that they act as the acid or the base in the reverse reaction. So H3O plus will lose a hydrogen in the reverse reaction. H2PO4 will gain a hydrogen in the reverse reaction. So the conjugate acid and base are just the acid and base of the reverse reaction. So CO3 2 minus, its most similar pair. Yep, HCO3 minus. So that makes this the base. Right? So we said bases always gain the hydrogen. And then that means that the HCO3 minus acts as the conjugate acid. So in the reverse reaction, it'll lose its hydrogen ion. Then looking at the other two, H2O becomes OH minus. So what happens to H2O? It loses its hydrogen, right? Goes from having two hydrogens to only one. So that means it's a acid. So then on the product side, its pair is the conjugate base, because it'll gain the hydrogen back in the reverse reaction. So last one, H3PO4, most similar pair. So notice again the phosphates. So you see you're just trying to pick out the ones that look the most similar, and you're just looking to say, okay, did it gain a hydrogen or lose it? So this one did what? It lost, which makes it a acid. And that means its pair is the conjugate base. Looking at NH3, it becomes NH4 plus. So it gains, so that makes it a base. Gaining a hydrogen makes it a base. Now its pair is the conjugate acid. So you really don't want, you shouldn't miss any of these questions. They're really not hard. It's just a matter of remembering what happens to an acid and what happens to a base, right? So you got to remember acids lose their hydrogen ions, bases always gain a hydrogen ion. And then on the opposite side, whatever the acid is, its common pair is the conjugate base. Whatever the base is, its common pair is the conjugate acid. So, in fact, water molecules form ions. They are some of the weakest acids and bases known. So if you have a collection of water in a beaker, there are very, very few water molecules that actually split into ions. So if you look at this first one, do you see that the first water molecule acts as an acid because it loses a hydrogen?
How do we create or complete a reaction?
Oh, you don't have to do that. That was another one of the things that I said. So you don't have to worry about completing reactions. I know you appreciate that. Because the only ones you would have to complete would be like strong acids and bases. But just the example of HCl and sodium hydroxide is pretty much the only one in a neutralization reaction. So in these, this is really talking about some seriously weak acids and bases. So water, if you have a container of water, there is actually a few water molecules that will form ions. So in this, do you see that the first water molecule acts as an acid? Because it actually loses a hydrogen ion and forms the hydroxide. The second one acts as a base because it takes that extra hydrogen ion on and forms the hydronium ion. Now, remember when I tried to put the water on the light bulb apparatus, it didn't light, right? So we said, oh, it's a non-electrolyte. But in fact, it's a really, really, really small amount, okay? So we're talking about the amount, if this was 1, this is about 0.00000001. It's a very, very, very small amount. But they were like, oh, it does have some. So this led to this understanding that acids and bases are really relative to each other. If you have a solution and you have more hydrogen ions than hydroxide ions, then your sample is acidic. If you have more hydroxide ions than hydrogen ions, then your sample is basic. And if they're exactly equal, like this, the amount of hydrogen ions and hydroxide ions, the H and the OH, if they're exactly equal, then that's neutral. So that led to the development of the pH scale. So they knew that water forms ions, but it's very, very small amounts. And they knew in this, like I said, so they said this is neutral because the amount of acid and base are exactly the same. The amount of hydrogen ions and hydroxide ions are exactly the same. Things that are acidic have more H plus or more hydronium ions and less hydroxide ions. So that it's an unequal number in comparison. Things that are basic have more hydroxide ions than hydronium ions. So then they started looking at relative concentration. The higher the concentration, the more hydrogen ions you have, or the more hydroxide ions you have, the stronger the acid or base is. The more ions you make. And they said, well, if the scale, in water, so in H2O, they say that it has 1 × 10 to the -7th molar H3O plus. So remember, molar is moles per liter. So that capital M is now a concentration. So trying to talk about concentrations of acids or bases from this 1 × 10 to the -7th, a really low concentration, they said, well, let's use what's known as a log scale because log is on powers of 10. So if you have 10 to the 0 and you put a log version and you take the log of it, that would equal 1. If you have the log of 10 to the 1, which would be 10, then you would end up with 2. So I want to practice this first. Has everybody got a calculator? You need a calculator. Okay? Because you want to make sure that you know how to put this in your calculator for a test, because this is really like the most complicated part of it, is making sure you know how to put it in a calculator. If we want to look at the pH of pure water, which most people know the pH is 7, the way that you calculate this is you want to put minus the log of the hydrogen ion concentration, or H3O plus. So you have to hit the plus minus button. So everybody knows the plus minus button is the one next to the equal sign. Okay, so hit equals, hit clear a couple times, hit negative, or sorry. And this one we have to do it backwards. So we need to first put in the exponent. So we have to put, if you're using the old calculators, an old calculator, you have to put in the concentration, then hit log, and then the little plus minus button. So the concentration for water is 1 times 10 to the minus 7th. Do you remember the EE button? So to put this number in, so to put in 1 times 10 to the minus 7th, you're going to hit 1, then the EE button, and then 7, and then the plus minus. So you're going to go, so it starts off, you hit 1, then the EE, then 7. Do you see the 7's like the little 07 up in the upper corner? Then hit the plus minus button. So it should now look like 1 and a minus 07. Does everybody see that? So it should have a 1, a minus, and a 07. Now push the log button. The log button is up in the very top, the middle button. You should now see a minus 7. You got to make that positive. So your answer is 7. Everybody get it? Mm-hmm. So put in 1 EE, 7, negative. Mm-hmm. Now hit log and the plus minus button again. That's it. Okay? So write your steps down. Mm-hmm. So 1, 7, now this, because you need to make it a negative. Okay? Now hit the log. Mm-hmm. And then the plus minus one more time. So that's how you get the answer for it. Did you know how to do this one on yours? Mm-hmm. Okay. Just want to make sure, because you're the only one with the fancy hat. Did you get it? Mm-hmm. Yes? Okay, good. Just follow this step every single time. So in pH, so they said, oh, so this is going to take a number with a lot of decimal places and change it to a whole number. So now we can take the log of an acid or a base or something that is neutral and be able to compare it. So pH scale goes from 0 to 7 to 14. Anything below 7 is an acid. Acids are pHs below 7. Bases are pHs that are above 7. So an acid has more hydrogen ions than hydroxide ions, so its concentration is going to be somewhere between 1 times 10 to the minus 0 to 1 times 10 to the minus 6. But bases have a lot less hydrogen ions, so their exponent numbers get bigger and bigger and bigger because you have more and more decimal places. And if it's exactly equal, if the amount of acid and base is exactly equal, then that is where you end up with the neutral pH exactly at 7. So let's look at some just examples. So looking at the pH scale. So there's your max, 14. Here's your minimum, 0. Now notice there is one that says -1. That is not naturally found. So they originally came up with pH based on things that were found in nature. So everything 0 to 14 fits if it's a natural substance. If it is a man-made substance, we can make things way more concentrated than would be naturally found. So that's like concentrated hydrochloric acid is like a pH of a -1. But that's because it's like below the scale. It has way more hydrogen ions than normal. So that's where that number comes from. Everything that is in the range from 10 to 14, things like oven cleaner, hair remover. Has anybody ever used Nair? Like that lotion? Okay. What did it leave your legs looking like? Well, one, there's probably no hair. But like, if you have sensitive skin, what does it like do to your skin? Really irritated and red and itchy. Okay. It's actually because it's a strong base. It's almost like putting lye on your skin and then waiting for it to dissolve the hair, because that's why the hair falls out. Is that base actually dissolves the hair, causes the hair follicle to unwind, and that's why you rinse it off. But I know a lot of people that like tried to use that in high school and they had like flaming red legs because it's very irritating. Have you ever used like Easy Off oven cleaner? Okay. What do you wear? What do you use when you clean the oven with that stuff? Gloves, right? And so like everybody now has self-cleaning ovens, but this stuff, like you had to heat up the oven, you had to spray it on, close it up for a few hours, and then you were like, hold your breath. You're like, and then shut it and be like, okay? And like if you didn't use gloves, your hands would be like all red and irritated. Yeah, like super strong. That was like one of the chores that we had when we were children. I mean, we weren't really children, we were teenagers, but you know, at that point, my mother's like, I'm not doing that, you do it. Okay, so these ones, think of these as being like very strong, concentrated bases. Coming in contact with them, strong acids and bases have a lot of hydroxide ions or a lot of hydrogen ions, and they're very irritating. Same thing down on the far end. When you're looking at things that are in the pH range of 2, 1, and 0, stomach acid down here, you would say that these are very strongly acidic. Strong acids and bases. Those that are on the extreme ends of the pH scale tend to be very corrosive.
So like that's why when you throw up your like throat and stuff.
Yeah, it burns. And people, unfortunately, people that are like the bulimics that like vomit regularly, they will actually begin to wear away the enamel in your teeth because the acids in your stomach are strong enough to dissolve the enamel in your teeth. So they end up with like loss, like enamel loss, which is
That's what I tell you to brush your teeth after you brush.
yes, like rinse your mouth out, try to get like the acid out. And so really vinegar is kind of like on the end of like the mildest end. But even that, my little nephew, I have a nephew and he has 3 older sisters and they used to feed him lemons all the time. They thought it was hysterical to watch his face. Well, then he got like kind of grew this like, he liked lemons after a while. So he'd take lemons and like stick them on his teeth like people would put an orange slice in their mouth. And they went to the dentist and he was like, he is not going to have any teeth if you keep doing this. Like you have to stop giving the kid lemons because he was like, his teeth are turning into little nubs because it has the ability to dissolve the enamel on the teeth. So things on the extreme, think of them as corrosive, reactive with body tissues. So you really try to limit your exposure to them. The closer you get to 7, though, the milder the acid or base becomes. So if you look like right above 7, blood, the ocean, baking soda. Some people brush their teeth with baking soda because it's sort of a whitener and it kind of scrubs stuff off your teeth. So here, these are what they call a mild base. When we can handle them, come in contact with them, mild bases, mild acids make less ions, which means they're not as corrosive. Same thing going down. So going down the list, below pH of 7, going down under 7, saliva, milk, rainwater, coffee. So those not very reactive, they are considered the mild acids. And in fact, most of your foods are mildly acidic or basic. Mildly acidic or neutral. The only real basic things that I can think of, if you ever had okra, okay? Like if you ever had like whole okra, how's it taste? Slimy. Right? Just like, remember I told you that the ocean feels slippery on your skin? Okra tastes slimy because it's slightly basic. Okay? If you've ever had eggs that aren't completely cooked and they're real soft, they're kind of slimy as well. They're about like 7.3, 7.4. They're a little bit basic. So those ones, there's not a lot of examples of basic foods that you actually eat. Those are really the only two that I can think of. But most of them are a little more acidic. So tomatoes, all your citrus products, all are going to be on the acid side of things. So soda, soft drinks, beer, wine, all of those are also on that acidic scale, but they're mildly acidic. So they don't cause damage to tissues if they come in contact. So just remember that the mild acids and bases, they're not as corrosive, they're less corrosive. Although I had a friend that like could not eat tomatoes because like that would also cause acid indigestion for him. A lot of tomato-based sauce would always cause troubles. So I mean, I might blame that on like, the salsa at El Tap, but I still go eat it. But right? So they tend to be less corrosive. These are more common in foods. Things that are slightly acidic, slightly basic, just above 7, just below 7, or the things that are R7. So next time what we'll do is we will do a couple more practices of determining like the pH and the hydrogen ion concentration. And then we can finish up this chapter by talking about buffers, which is sort of an application of acids and bases. So we'll finish that part next time. So like I said, I didn't think it'd be much more, probably like another 10, 15 minutes. Then we'll go on to chapter 10, okay? So I did talk about the schedule for anybody that came in a little bit late. I did talk about the schedule. I'll have this exam graded and I'll give it back to you on Wednesday night. So tonight we pretty much did acids, bases, equilibrium. We did pH. So now on Wednesday, the plan is to finish chapter 9 and then go ahead and start chapter 10, which is proteins. So we got to talk about protein structure and then we'll talk about what proteins do. Probably won't finish that till the following Monday. And that'll give us time like to make sure we're all done chapter 10. Might start chapter 11 that Monday. I don't know. But what we'll cover in chapter 11 is kind of, again, like kind of a little more stunted. So we're going to talk about in chapter 11, really just DNA structure and function.